Often we think of acids as being very corrosive, very dangerous. We want to stay away from them. But have you ever considered that there's other acids as well? Vitamin C is a citric acid, and it's very important in our diet in helping us to stay healthy. This is also a type of acid. So we have what's called an operational definition. This is a definition that describes what something is or what it does, not why it does it. Okay, so the what is a measurable quantity. The definition can apply to most situations. Okay, and so for an acid and base, try to think of, as I described the next example, of what is the operational definition of an acid or base. What does the acid or base do? Okay, or what is it? Let me take us to a common example that we know of and that we all understand, and that's the definition of speeding. And we've all seen this in this country. Well, any country you see speeding. So an operational definition of speeding is going fast, going 100 kilometers per hour, going 20 kilometers over the speed limit. Okay, all of these are operational definitions of speeding. It's what it is or does, not explaining why it does it or how it does it. Okay? The best operational definition is the one that we can measure. Okay? It is the definition that would describe most cases. So the one that we can measure in this situation is going 20 kilometers over the speed limit. Because as you know, going fast, okay, is fast in one environment, may not be fast in another. Going 100 kilometers is not speeding on some streets. But if we go 20 over the speed limit, we can measure that. And it is we could use it as a definition of speeding. And every time we are 20 kilometers over the speed limit, we are speeding. So this would be a good operational definition for speeding. It is measurable and it applies to most situations. A conceptual definition. It explains why the operational definition occurs. So in our speeding is why is our car moving 20 kilometers over the speed limit? That will be the conceptual. Conceptual is an idea, a thought. It usually explains using other concepts or other ideas. For example, let's go back to our speeding. Okay, the conceptual definition of speeding is why does the car speed? Okay, and one conceptual definition could be the gas pedal is pushed close to the floor, increases the amount of fuel going to the engine, causes the engine to rev higher, then causes the axle to turn faster, making the wheels rotate more, propels the car forward until the car is moving beyond the speed limit. This would be one example of a conceptual definition. Okay. So when it comes to acids and bases, an operational definition would be what it does. Okay, what are some of its properties? Okay, the conceptual definition is why does it have that property? What is unique about acids that makes it obey some of these properties? For example, some of the properties of acids and bases is they taste sour. Okay, usually they have a pH, such as lemon juice, pH of 2. Acids usually have a pH below 7. And we'll talk about pH later in the unit. They feel dry and itchy on your skin. These are all operational definitions. Okay, what the acid does. It doesn't explain why it makes your skin dry. It doesn't explain why the acid tastes sour. It's just what it is, what the property is. Acids have a pH less than 7. Okay, pHs that are closer to 0 tend to be what we call stronger acids than acids that are closer to 7. Another property of acid is that they turn pH paper red. Blue pH paper, when placed in an acid, turns red. And you can see this in the image, over here. I have to get my pen working so I can highlight on my pen. So you can see over here, this is what we mean by blue pH paper. You may have played with this in high school, or if we were doing labs, you would definitely see it in the lab, as we would have introduced you to that. It neutralizes bases, and we'll talk about bases in a minute. Neutralize means it brings it so that it's no longer an acid, no longer a base, it's in between. Okay, this is usually pH 7 if we're measuring. pH is a scale that's used to measure how acidic or how basic a solution is. But we will talk more about that later, just so you can understand what it is. And as we probably already saw in that video of the sponge, and that we already know, is that acids are corrosive. They can burn skin, they can burn wood, they can burn metal, and that's why they're often very dangerous. Acids can conduct electricity. Remember, we talked about solutions that conduct electricity last unit. We called them electrolytes. Well, acids are electrolytes as well. Some are strong electrolytes and some are weak electrolytes. Depends on how strong the acid is. Acids are able to react with metal, one of their corrosive properties. They actually react with the metal and actually can, what we see, burn a hole in it. And as you can see in this picture here, that's the acid reacting with the metal and one of its corrosive properties. So what are some so what are some operational definitions of acids based on what we just saw, some of their properties? Remember, operational is just what it does. It's not explaining why. Okay, so some of the operational for acids: it has a pH less than 7. It can turn blue litmus paper red. It conducts electricity. Okay, all of these are measurable. We can see it. Conceptual definitions explain why acids do these things using known concepts. So to develop a conceptual definition of an acid or base, we have to look at why does it have a pH less than 7? Why does it turn blue litmus paper red? And why does it conduct electricity? Okay, so some of the conceptual definitions that were developed over the years were developed by many scientists over the years and have developed as we learn and understand more about chemistry. One of the first scientists to develop a conceptual definition that the chemistry community recognized as being fairly accurate was Arrhenius. And so we will have Arrhenius definitions, and his definition is a conceptual definition. We'll look at that one today. And then we have the Bronsted-Lowry definition, okay, and he developed the conceptual definition to a little more detail, and it works a little bit better. We'll look at that one next day. So that's acids. What about bases? Bases have many properties as well. Okay, they taste bitter. Okay, if you've ever tasted soapy water, okay, that's what bitter tastes like. Baking soda, okay, if you've ever tried that, tastes bitter. Both of them have a pH above 7. Bases tend to feel slippery if you get them on your hands, okay, such as soaps. That's why soaps are slippery, because it's a base. Bases have a pH greater than 7. The higher the pH, the stronger bases. pH usually goes up to around 14, maybe sometimes a little higher, but usually 14. Closer to 14 the pH is, the stronger the base. Bases, as you can see in the picture right here, turn red litmus blue. Bases blue, BB is one way to remember it. Bases can neutralize acids. Acids neutralize bases, bases neutralize acid. That means it brings its pH closer to 7. Bases can also be corrosive, so they can also burn skin, burn wood, burn metal. And bases are also good conductors of electricity. They make electrolytic solutions. They can conduct electricity. So based on the properties, some of the operational definitions of bases, or what bases do, could be summarized as a pH greater than 7. They turn litmus paper blue, they conduct electricity, etc., things like that. So we take the properties of the bases and we use it to turn it into a definition. Okay? Now, let's look at some of the conceptual definition. Okay? The conceptual definition of a base is, why does it have a pH greater than 7? Why does it conduct electricity? Why is it corrosive? Okay? So the first scientist we're going to explore his operational or conceptual definitions is Arrhenius. Okay? Arrhenius' definition was based on dissociation. And if you remember from Unit 4, dissociation is when an ionic compound breaks up into ions. So as you can see in the picture right here, we put HCl, which is a base, hydrochloric acid, an acid, not a base. Hydrochloric acid, when we put hydrochloric acid in water, it breaks up into its ions. Hydrogen ions will be found in the solution, and chloride ions found in the solution of water. But so Arrhenius said acids ionize in water to form H+ ions. So this is his definition right here of acids. Acids ionize water to form H+ ions. And you can see that in our solution on the right of hydrochloric acid. Some of the things required for Arrhenius, that the acid must be aqueous. It has to be in water. So one example is the HCl. And when we put it in water, make it aqueous, we see that we have hydrogen ions and chloride ions. Another acid is H2SO4. We put H2SO4 in water, it breaks up into ions, and we get hydrogen ions and sulfate ions. It's the hydrogen ions that make it an acid. Arrhenius' bases were very similar. He said that a base ionizes in water to form hydroxide ions. Again, the base must be aqueous, so it must dissolve in water. Okay, and some examples: sodium hydroxide, we write the dissociation equation, and we see we have hydroxide ions. Calcium hydroxide, not completely soluble, but it is to a little degree, and we see we have hydroxide ions. Okay, so both of these would be examples of a base. So that ends today's recording. It's an introduction to acids and bases. And we looked at Arrhenius' conceptual definition. So we have the properties of both and the operational definitions and Arrhenius' conceptual definition. Next day, I will post a recording on Bronsted-Lowry's definition and conceptual definition, which is much more useful, you'll see, than Arrhenius. So thank you for watching today. If there was anything you missed, didn't understand, feel free to rewind, and have a great day.